So we're not doing Hooke's law because that's my other class. Oh my. Well, in the middle of all this, my wife's new laptop arrived in the mail finally. We used our stimulus checks to buy her a new laptop, and then a month ago, and they delivered it to an address in New York where we haven't lived in years. And it finally, Apple, they'd say, oh, they're the big technology people. It was so difficult to get them to fix it. So they just said, all right, instead of waiting for some kind of refund to come, we're just going to send you a new one. And it finally arrived. Okay, so oscilloscope lab. All right, so so you guys hopefully you played with these sims. And so I got this one here. And the bottom line is that an oscilloscope is basically a time-dependent voltmeter. And so it's set up so the dot goes across, and then you connect up the voltage, you change the sensitivity, and then you notice that let's see if it changes on the screen. Oh no, it doesn't do this screen either. I wonder why not. I thought it would show something on this screen. But again, the bottom line is it's a time-dependent voltmeter. And so let's see. Now we don't get that nice picture of the dot being deflected, unfortunately, and we can't change the time base. And then you get to play a game and see. So you need to learn. So the trick is you change this and then you count boxes. But in principle, you know that, but we'll go over it. Okay. So let's just go through this. What we're going to do is we're going to do the beginning parts with me because I have a real oscilloscope here. And I showed you this a little bit last week. And I have a real function generator and a transformer. So there's a transformer down here. So then you can see these things in what happens with the real ones. And then we're going to go through, and once we get to a certain point, I'm going to hand it over to you guys. Right? Because then there's the function generators. So you guys can do that in Tinkercad. All right. So as we do these steps, they want you to make sketches in your logbook of what you see on the screen. And in the real world, I provide these to students. I even print some of them out so they can sketch these things during lab class and paste them in. But I'd like to see you guys just have sketching by hand in your logbooks. But this is the kind of thing right here. And notice these two lines that go up and down across the middle and then up and down in the middle. Those are very useful lines that we use all the time. Excuse me. Okay, so first, I can't remember if the pre-lab has these definitions, but they're really critical. So, especially for the sinusoid, that's for you guys as 1,200 students, that's really the most important thing. So let's put this knowing how to apply it to a triangle wave, for example, is something that we would say that a 1200 level student has to deal with. So anyways, we have the voltage peak to peak. So VPP, V peak to peak, if you will. And so that's just from, as it states, from the positive peak to the negative peak, or the negative peak to the positive peak. You know, you say tomato, I say tomato. Or if your glass is half full or half empty. And then we have the V amplitude. And that's just the V peak to peak divided by 2. And we have that because if you think of this as a sine wave, and let's say this is time here, and you have, remember, there's this thing omega equals 2 pi times the frequency, and frequency is number of cycles, number of wavelengths, if you will. Number of waves per second. And omega is in radians per second. So hopefully you remember that from Physics 1100. Oh, and once again, I forgot a really cool video to show you how circular motion and sine waves relate. I'm going to find it and post it. So if I think of the, let's see, this is voltage, whoops, on the y-axis. So the voltage that you see on the screen as a function of time equals sine of omega t. So this would be the equivalent of 90 degrees, you know, pi over 4, 180 degrees. And then, of course, since sine only goes from -1 to 1, we need to multiply by an amplitude. So when you're at, say, 90 degrees, that's the amplitude, see? That's just where it comes from. And then there's this thing called RMS voltage. And we don't spend a lot of time with it with you guys, but the RMS was invented, but what does it say next to cycle? Oh, sorry. I'll make that better. Yep, sorry. Okay, so one cycle is one wave, or one wavelength, if you will, right? Start to finish. Does that make sense? So then, yep, so a frequency is number of cycles per second. How many times does it repeat? Or how many waves, number of waves per second. So if I multiply that by 2 pi f, I get radians per second, because there's 2 pi radians in one cycle, because this is from 0, 90, 180, 270, 360, or pi over 4, pi, give me a minute, I don't want to screw this up, pi over 2, pi, 3 pi over 2, 2 pi. There we go. So it all fits together. It's really amazing, Mother Nature and circles and sine waves. So V peak to peak divided by 2. And this was developed by engineers. So if we say that a battery is going to deliver a power equal to VI, and this is DC, direct current, equal to, what is that? Let me think, 3.5 times, yeah, let's say 3.5 watts. So then that's at 5 volts. Now let's say I have an AC source. So now if I say my AC source is 5 volts, it's got an amplitude equals V amp. Its VRMS equals 3.5, basically. Multiply 0.7 times 5. It's a little different. So then you see how I get now power equals VRMS times I equals 3 watts again. 3.5 watts, sorry. So if I wanted to deliver the same amount of power as the battery at that 3.5 watts and 5 volts, I need a 5 volt AC signal. That's where it comes from. And that's why we bother. And there's math behind it, but it's not super important for you guys. Root mean square. Engineers use it all the time. But it's important to know what your instruments are measuring. So I'll give you the advanced organizer. Oscilloscopes do V peak to peak best. And voltmeters they measure VRMS. And in fact, voltmeters might be limited too. They might be, say, they might be frequency limited. When I was your age, you had to spend a lot of money to get one. First of all, for the most part, they do 60 hertz for obvious reasons, because electrician needs to measure, or you need to measure the voltage of your outlets. To get one that did, like, say, let's see, back in the day, back in the day, only 60 hertz. Nowadays, you can buy, if you wanted to go, let's say, 40 to 10,000 hertz. Back in the day, that was hundreds of dollars. Today, it's $25. I have one. So it's always important to know what your voltmeter is telling you. Most likely it's RMS, and then you have to look at it. And for the most part, your voltmeter And I don't know, this one says true RMS. So that means that it can do a range of frequencies. And this thing, I bought it on Amazon for $25. Amazing. I can't believe it. I thought I'd have to spend a lot of money on one. Okay, so I think we can dig in now. So this is mostly about a step-by-step, and I'm going to ask you guys just to do a small short report about when we look at the real components, and I mean when you look at capacitors and resistors, this basic stuff. And it's perfectly fine to say, all right, this is now step part A, step 1, step 2, step 3. It's a really easy way for you guys for you to go back later on and figure out what exactly you were doing at the time. Oh, excuse me. So let's see. Let's put this off to the side so I'm going to be able to read my manual and give you guys as much screen real estate as possible here of what I'm doing. Oh, that's really weird. Ooh, focus. I don't have the overview camera turned on. There we go. So I'm looking at the output of a transformer at the moment. So all oscilloscopes have basically the same controls, and you have in the manual pictures of these things. So this has 2 input channels, and you can change the sensitivity. This is at the best it can do. It's going off. The transformer is putting out a lot of volts. So you can change the sensitivity. You can change the time base. And at the end of the day, oscilloscopes are really versatile. And it takes some practice, though, and you get a feel for them. And it's too bad. Students really love playing with these things. And then there's what's called triggering. So triggering, when it comes to a signal like this, is not super important, but I'll show you what it does in just a minute. So I just wanted to show you the basics. So you have the beam quality here, where you can change the brightness. What happens is that the slower it goes, it tends to get pretty bright. So then you need to turn it down. And then as it goes faster, it gets dimmer. It has to do with the dot hitting there, and then how long there's a chemical called a phosphor that's glowing inside. And then there's a focus knob. Then you have the section for vertical stuff, and so that's about how many volts per box, and we'll get back to that. And there's 2 channels possible here. I'm only using 1 at the moment. And then there's the x-axis, the time axis. So you can change here, and then triggering. And that's to say, when should and the triggering is telling the oscilloscope when to start making the little dot go from across the screen. Okay, so we're not supposed to put this on just yet. So let's take a look. The trigger coupling to AC, well, yeah, we don't, that's just, well, I'll show you what that means eventually. We just, right now, just do what it says. When I put it on auto, so that means it just goes across. See, well, it doesn't care. I'm not triggering it. Let's see what happens without this. Ooh, what was that? Well, it wasn't my mother, so that's a good thing. Okay. It was this. My neighbor, when I brought Hannah's bus home, my neighbor gave me this. Guy, he's like the mayor. He knows everybody in town. Oh, I'm getting some glowing on the reflection of the windows. Let's see. Can I get rid of it? Oh, no, I know what that is. It's this other light. Hold on. Okay. Okay. That's better. No more glow on there. All right, so what does it say? 5 milliseconds per centimeter. Okay. So it's at, yep, that's what it's at. Excuse me. Set channel 2 to ground. Oh, it should say channel 1, but it doesn't matter. To you guys, you're not here. And 1 volt per centimeter. Okay, that's done. You can't see that so well because it's shining on there. There we go. Now you can see it. And you can sort of see the 1 to 5 milliseconds per box. And there's the 1 volt per centimeter. Set source to channel 1, which it is. Okay. Now, right. So that's this is what you always do. You set this up. So we want to focus to get that line as narrow as we possibly can get it. Yeah. And then in general, you make it as dim as you can get it. That shouldn't have any effect. And then center the line vertically. Position knob. Okay. And yeah. Okay. So observe the sweep motion. So this is what happens, as you might have noticed from the pre-lab. And the camera isn't fast enough. I can see a little dot running across the screen. It's a little too bright, so I'm turning it down. So let's see if I can slow it down so you can see a little dot. Yeah. And I think that's the limit of how slow it'll go. Yep. And now, if I were to, oh, I know what I could do too. If I had a little battery, let me grab a battery. Here we go. Yeah, I can see where in the we should supply the students with a battery. So you can see now I've set this thing to, so now you can sort of see some stuff going. It's getting a little fuzzy. Yeah, when I touch it with my fingers. And then also if I touch the battery to it, we can see it go up. Oops, where'd it go? Yeah, you see then it holds steady up there. It's 1.5 volts. So I'm surprised it's not going up by 1.5 boxes. Oh, because I didn't get this. Oops, wrong one. 1 volt. Let's speed it up. Okay, so now it's right in the middle. So I connect a 1.5 volt battery. Let's see how good of a battery we have. Oh, it's at ground still. I gotta connect it. Now you can see some of the noise around us. And there it goes. That's a little more than 1.5 boxes. Good battery. Cool. Okay, so let's see what it says to do. Observe the sweet wiggle. Oh, yeah. So just, I'm thinking of students that are doing this on their own. So I tell them to set it slow, and then you can sort of wiggle this up and down, and you can kind of get the idea of it as a sine wave. But it was easier. Well, we'll see in a minute. We'll see real sine waves. Okay. So let's see. Let's get it back and let's center it again. All right. So what does it say to do next? Pick up from the room. Okay. So I've got this wire just attached. You see it wiggling, and it's actually got two ends. One is the ground though, so it doesn't do much. But the red one is directly connected to the little dot. And so if I start to observe things, I see, well, something's going on there. And we saw this last week. And holy smoke, look at that, huh? And you notice it's walking across the screen. And also it's a trip. If I touch it, it explodes, right? And kids have fun holding hands. And they see if they hold hands, they can make the signal get even bigger. Now, if I change it to line triggering, you notice that it no longer walks across the screen. It stays steady. And what that is happening there is that of course, it's triggering on the frequency of the where the object is plugged in, which just of course happens to be 60 hertz. Now I've connected it to an antenna I have out the window, and you can really see that the 60 hertz noise is the bane of our existence. So let's just put this back here. And I'm not touching it anymore because I want to see the other stuff. So even if I bring my hand close to it, notice it gets bigger. So what does it say now? Try switching from internal to line. Yep. Oh, it says sketch the waveform. So there. Let's wait a minute. And just going to make a slight adjustment. And remember, there's 5 milliseconds per box. So you can count 1, 2, 3. Well, I guess I can draw this on the computer screen. So make a little sketch of this, just this blue area. So notice we're here. 1, 2, 3. And there are little hash marks there. Yeah, 0.2, so it looks like 3.3 boxes. Because you notice it's 2, 4, 6, 8, 10. and it's 5 milliseconds per box. 5 times 10 to the minus 3 seconds per box. 3.3 boxes. So I multiply them, and the boxes cancel out, and I get 15 plus 1.5 is 16.5 times 10 to the minus 3 seconds. And so that is the period, right? We've learned about that. It's the time it takes to repeat. That's the period. And the period equals to 16.5 times 10 to the minus 3 seconds. So then the frequency equals 1 over the period. And guess what that is? And I get 60.6 hertz. Well, and the house is at 60 hertz, lo and behold. So 60 hertz noise, that's everywhere, unfortunately. Excuse me. Okay, it's okay if I change things. Everybody got a sketch? Well, I know what I can do. I'll waste a little time by turning on the overview camera so you can see what I'm doing. Better see what I'm doing. Oh, good. I see. Thanks, Carl. Now I've got my headphones back on. And thanks for the feedback. Alright, what's next? It's hard to pick up with the phone. Okay, I measure the period, so I showed you how to measure a period. Does everybody understand how I measured the period? Well, let me go through and do it the official way. So what you generally do, so we have So we take one spot, we look at our waveform, and we notice there's a repetitive pattern there. So we pick a convenient vertical line. And then we want to take advantage of those hash marks, I call them. And they're everywhere, but they're easier to see down below there. So now I can see 1, 2, 3, and there it's. I think it's more obvious now why I picked 3.3. But this is a great demonstration of the versatility of an oscilloscope. So what you do is you twist the knobs until the picture looks pretty, literally, and then you read off numbers from the dials. So again, I have 3.3 boxes. They are centimeters. And then over here, in the time section, I see 5 milliseconds per box. 5 times 10 to the minus 3 seconds per box. And that's how I measured the period. So make sure you've got something written down there. So you make a pretty picture. Basically, you like to see a couple of wavelengths. We have two, 1, 2. We have 1, 2. Well, I have like 2.5. Even though there's 3 peaks, it's the repeats, right? We have to. So we have the 2 repeat points, and also vertically it fits on the screen. Well, it did, not anymore, but we make a pretty picture which shows us a couple of wavelengths, and then we can start taking measurements by moving it around the screen to take advantage of the center lines. And then reading off, and then counting boxes, and then reading off the values per box from the dials. We'll get into the vertical part soon, because since this is noise, it's kind of and it's going to change all the time. We'll give it a sine wave, and then we'll see it better. Okay, so the other thing, just that students are always amazed, and we saw it last time, is that there's wiggles within wiggles, huh? So I speed, and we can already see some wiggles within the wiggles. And now we speed it up, and we can see there's this, whoops, this wiggle. We lose it a little bit there, but here it is. So there's that wiggle. You can sort of see the peaks. But of course, there's other wiggles within those wiggles. I like this one, because now, well, oh, too bad it's not focusing very well. You guys can't see what I can see, but no, it's close. So now you can see there's this sort of wave like this, but then there's this jaggy wave too. So this is a nice one. I will give you a minute to sketch this. And this is at 0.2 milliseconds per box. So these here, this, let's just for the sake of argument call this 0.2 milliseconds, one box. So that's, wow, let me do how many hertz is that? 0.2 E3. So that's 500 hertz. And these little ones, maybe they're 0.2 times 0.2. So that's 0.2 boxes times 0.2 millisecond. Oops, per box. 0.04 milliseconds. And that is 1, 2, 3, 4, 25,000 K. That's 25,000 hertz. Heaven only knows where that's coming from. What's fun is when you have those big fluorescent lights in the classroom, I show the students how we turn the lights in the room off and on, and you can see this. It's amazing. I tell them the story about how when I was a master's student, I had this strange noise was affecting me all the time. And one day I turned around and I turned off the lights in the room. I turned around and I noticed I'd left the oscilloscope on. And I turned the light back on and I said, well, wait a minute, look at that. And then I flipped the lights on and off. And I've been trying to find this noise for months. And it was just the fluorescent lights. I was so pissed at myself. But the definition of wisdom is that you've made all the easy mistakes. And in fact, this oscilloscope is kind of limited, but it can go. But you can see some pretty high frequency stuff in here. There's even more wiggles within the wiggles. Look at that. And this is in microseconds now. So those are inside there. You can barely see them. That's megahertz. So now we're getting to radio, like the local radio stations. This one can't pick up on the cell signals, but it can do the megahertz is the local is an AM station. I don't know what let's take a look and see what the USB oscilloscope can show us. Oh, so it can definitely show us other frequencies. And I can't do line triggering with this. So that's interesting. But this thing can really show us. Yeah. Really, we're at. It's amazing. So let's see. What is that? I want to see what that frequency is. I can use I can cheat. Oh, it's not showing me the measurement. Oh, that's in angles. I want seconds. Here it is. I forgot. I don't know what the first one is. 1, 2. So that's, oh, it's not telling me the frequency. Ah, here it is. 1.5 megahertz. So that's radio 1580. I mean it too. And then you see these other ones here. I don't know if this thing can do cell signals. Oh, holy crap. It might. There they are. I think those are cell signals. Is there we go. I'm not positive. Whoops. Sorry guys, I love to play. This is, oh no, it's an FM station, 88 megahertz. Okay. Cool, huh? All right, so let's get back to the task at hand. I'll plug it back into the analog scope. Okay, what's next? So let's take a look. We measure the period of the dominate noise and calculate its frequency, which we did. Now it wants us to look at the transformer output. And it went off the screen, so we just, once again, we adjust it. It's not a perfect sine wave, this transformer. I don't know, something's wrong with it. And so, so they want you to make a sketch of this one. And we can take a measurement at the same time. So let's put this. We've got our convenient vertical line, and I like that little bump on there. And then, well, we don't want to mess you guys up. I'm going to leave that centered there. So let's see if we can figure out where it is. See if I can focus this better. That's as focused as it wants to get. So it looks like it's, yeah. I'll turn down the intensity, that's right. There we go. Yeah, so it's right again at 0.3. So just, I'll put it back in a moment. I just want to show you. Yeah, so it is at 0.3. So once again, it's 3.3 boxes. It's 5 milliseconds per box. What happened to my, oh, this is always on top, that's right. There it is. Put that down here. So once again, it's 3.3 boxes. And it's 5 times 10 to the minus 3 seconds per box. So we once again get 16.5 times 10 to the minus 3 seconds. Oh, there goes Jenny. And we want to measure the peak to peak. So for peak to peak, for voltage, we pick a convenient horizontal line. And this is the tricky thing. We have to get the trace. It has a certain width. So the practice is to get it centered, which is not easy. It's not, it can be hard, because especially these knobs are getting old. Oh, nice. And then we want to move and take advantage of our special line. So we've got 1, 2, 3, 4, 0.2, 0.4. Looks like 2, 4. I gotta look at the screen with my own eyes. Yeah, it's just above 4.4. So now we get 4.4 boxes times 5 volts per box equals to 20 and 2.0, right? 22 volts. Peak, 22 volts. So that's voltage peak to peak. Triggering, okay. Okay, so how does triggering work? This is a great way to see it. So I have it on line triggering at the moment. And so I can put it on internal. And I've got a button here that says if it's pushed in, I have negative slope. If it's pushed out, I have positive slope. So notice that the trace begins on a positive slope, and then the level knob tells me how much I want to get, how high it goes. There's a limit. That's interesting. I never saw that before. So, and then I could do negative slope. So it depends on the signal we're looking for. So triggering is not super important for us, but that's what it does. And way to see its utility is if I go back to looking at noise, and this is important for analog scopes especially. So then I can twist this trigger knob. It's not really working. I wonder why not. What if I DC coupled it? Or I don't have it on normal triggering. That's why. Okay. So now you see it's picking up just that high spot. Why do I care? Well, if I want to, if I don't trigger, you see there's a lot of mess there. So what I can do is I can start to pick out the high spot of those 60 hertz sine wave, and then I can sort of keep it focused on just that. So now, and I can also trigger on just, it sort of cleans things up, right? So I can, it's kind of a filter. Again, it's not super important for you guys, but that's what it does. Okay, so let's go back to the transformer. What happened? Oh, right, I've got this way up here. And then trigger it. Cut down the, there it is. Alright, so there's our sine wave back. So now we know how to measure time. The period, you need this because you're going to do it in Tinkercad. And, okay. So let's everybody, you know the voltage peak to peak. Everybody please calculate the VRMS. So you have 22 volts peak to peak, Everybody write down what is the RMS voltage then. Calculate the RMS. I'm going to do it in my logbook. Get my handy dandy calculator going on here. All right, so of course this is leading up to something. So now I'm going to put my voltmeter here, and I'm going to measure the voltage of the transformer with the voltmeter. Try to get that out of there so I don't burn anything up. And then notice it says 8.3, 8.4 volts. 8.4. Okay, why does it say 8.4? Anybody have an idea? What did you guys get for the RMS voltage? Of course, I even told you what the voltmeter does earlier, right? Anybody, right? Say, I got 7 point. I got the same thing, Aaron. So what happens is the oscilloscope, an analog oscilloscope, can be a little tricky, huh? So the digital voltmeter, of course, is quite accurate. So let's take a look to, we use the digital oscilloscope here. We can get the final verdict. And I think another issue is that it's not a perfect sine wave. So let's see, clear drawings. And I hope I didn't close it, did I? Oh, no, I didn't. All right, let's run it. And we need to, let's see, we want to go back to milliseconds per box. That's interesting. Why is it showing me all that noise? Did I plug it into the right channel? I thought so. Yeah. There it is. So it is still showing us some noise. It can really show us a lot of things. And now you can see if the trigger digital scope, you see, lets me see backwards in time. So if I take these cursors, so this gives me a peak to peak of 23.1. So let's all calculate the RMS voltage now with 23.1 peak to peak. Yeah. So if you see now what you calculate now for the RMS is much closer to the 8.38. And my guess is that the discrepancy is because this is not a good sine wave, not a perfect sine wave. So that fools the voltmeter. They have to assume that when you input an AC signal, it's assuming it's a sine wave. Okay. So make sure you're writing this stuff down. So I can even do something clever here for you guys. And another thing that's cool about digital scope, you can stop it. All right. So let's see. Frequency 60 hertz. Oh, I know this will work. Hold on. Where is it? Snipping tool. New. There we go. Let's see at this cool picture. File. Save as. And where is this? This is in Zoom, huh? Oh yeah, that's right. So this is transformer on digital scope. So I'll send this to you guys. Okay. So those are the basics of oscilloscopes. And in fact, a digital scope a real one has the ability to put those lines on. I don't let students do that the first time they see a oscilloscope, because everybody should learn old school. But students generally find the old analog scopes pretty fascinating. Oh right, because I unplugged it. So this one isn't that old. We have some of them. Well, you see it's got this old property sticker, so that's back. We weren't the Golden Eagles when I was a student here. We were the Diablos. And I thought it was kind of racial when they changed it to the Golden Eagles, but they had a new board, a new university board, and they wanted to promote the university. I understood where they were coming from. I always think of myself as a Diablo, though not a Golden Eagle. But some of these oscilloscopes are older than me that we have lying around. Pretty old.